So let's start with the slide set number 2. And in this initial few slides actually talk about the topics we are going to cover in this slide set, and also gives you the relevant sections from the book and suggested problems from the end of the book if you want to practice on your own. So let's see what we have in this slide set. Just a reminder, last time we saw two types of systems. One was continuous time, two types of signals, continuous time and discrete time. And how do we represent it? And most of the real world signals are continuous, and we can get discrete time signal from continuous time signal just by taking samples. Okay, so here some very basic things about signal are covered. Let's talk about power. Power is an electrical signal which can be obtained by multiplying voltage with current. V multiplied by I gives you power. And from Ohm's law, we can replace I with V over T, so it can be V square over T, or it can be I square R, V square over R or I square R. So multiple different ways in which we can find out what power is. So if we talk about this power, and we have a plot of power signal against time, and we want to find out what is the total energy over a particular time interval, what we do is that we can sum up all the power values from time t1 to t2. If it is a continuous signal, summation will become an integral. So it will be integral from t1 to t2. And if you want to find out the average will be whatever total value we get divided by the total time duration. That will give you your average. So very simple common sense, we can just compute the values within a particular time interval, or we can find an average within a particular time interval for any given signal. Example was that of a power that we just saw. In this course, we are not going to limit ourselves to a particular type of signal, whether it is current, voltage, power, velocity, speed, distance, whatever. We are going to talk about generally a signal, and that signal can be plotted against time interval t. So x of t against t we can plot. So if you want to find out the energy in any signal, now we are not talking about any specific signal, any signal whose, let's say, graph is there or values are with you, we can find the total of that just by taking the integration of square of that signal. That is going to give you energy of that signal. So in general, energy of any signal would be sum of the square of that signal. And if you want to compute that energy within a particular interval, let's say from t1 to t2, we just take summation from that within that interval. And as I mentioned, if your signal is continuous, then continuous summation is integration. So we just take integration of the signal square. That will give you the total. And if you have discrete signal, x of n, then the energy would be summation of the signal square, x of n square, as I mentioned. And if you want to take the average would be that signal divided by time. So energy divided by time, we refer to it as power, or power multiplied by time is referred to as energy. That is from electrical perspective. But generic, any signal, we talk about energy of a signal, which is going to be sum of the square of that signal, or summation of the square of that signal. That is the energy. And power of that signal would be that thing divided by the time. The average power will be the total energy divided by total time. So this was just a generic sort of a thing. Now, if you want to find out the total energy from minus infinity to infinity, the entire time duration, the entire duration of that signal, from minus infinity to infinity, that would be again taking integration from minus infinity to infinity of x of t, and if it is discrete time, taking summation of x of n square from minus infinity to infinity. That is going to give you the total. And if you want to find out the average, we just divide that total divided by the total time. Now that actually gives us two categories or branches or subclasses of signals. And these two at the very first look kind of confuses people, but I will just explain. It's very common sense, simple thing. The two types of signal that we may come across, the first type is which has a specific or finite or quantifiable total energy and therefore zero average power. And the second type is where we have a finite or quantifiable average power and therefore infinite total energy. Now, what does it mean? So if we see any, uh, let's just take an example. Let me try to make it work. So if we see any, let's say, particular given signal, which starts from, let's say, time t1 and finishes at time t2. So what happens there? I'm sorry, Mr. So if we take any specific, let's say, signal which starts from t1 and finishes at t2. This is any signal x of t, it may be any signal. Now, if you want to find out its total energy, we just take integration of x of t square dt from time t1 to t2. And that is going to give us the total energy from t1 to t2. Now, this is a signal which starts at a certain point and ends or finishes at a certain point. And if you want to find out the E infinity, as we say, then we just take it from minus infinity to infinity, the same quantity, x of t, and we just square that thing. Now, in this particular case, E infinity is also going to give you a finite value, because we know that area under the graph of square of this signal would still be a finite value. Any confusion here? Very straightforward, simple thing. Now, the problem would be that here we have a signal which has a finite total energy, but if you want to find out the total power, that would be E infinity divided by total time duration, which would be infinity. So it will be finite quantity divided by infinity. What should it be? What should this value be? Any finite quantity, let's say 2 divided by infinity or 4 divided by infinity, what is it? It should be 0. 1 over infinity is actually 0, or any constant, any k constant value divided by infinity is equal to 0. So if you have a finite energy right here, then if you want to find out average over the entire duration, that average is going to come out to be equal to 0. Understandable? So let's take another example where we have, let's say, average equal to some constant. Let's take an example. If we have a signal whose value is a throughout, the signal x of t whose value is a throughout. So what will be average? Or let's make it more simple, if it is just 1. If it is 1 throughout, what is average? Average is just going to be 1. But if we want to find out its energy, it would be taking integration from minus infinity to infinity of x of t square, 1 square integration. What should that be? E infinity. It would be integration from minus infinity to infinity of, let's say, 1 square dt. What should that value be? Come on. It is summation. Summation of a continuum. If you are trying to sum up an infinite quantity, the value would be infinity. Let's make it more simple. Let's talk about discrete signal. So if we have, let's say, all ones going throughout, right, from minus infinity to infinity. This is your x of n. And if you want to compute what is your E infinity, it is discrete time, so it is going to be, let's say, n equal to minus infinity to infinity x of n square, right? Summation. What should that summation be? X of n always is 1, so it will be summation of n equal to minus infinity to infinity of 1. What will be? Summing up infinite numbers of 1. The value would be, come on, is that so difficult? Infinity. Because we are not trying to sum up finite values. In other case, if we have just values let's say 1, 2, and 1. This was your x of n, and this starts from, let's say, n equal to 2, 3, and 4. Rest all are 0. Here, if you want to find out E infinity, it will be summation n equal to minus infinity to infinity x of n square. You can open it up. We know that it is 0 throughout. Only for n equal to 2, 3, and 4, the values are 1, 2, and 4. So 1 square plus 2 square plus 1 square. So just 6. The value will be just 6, finite value, because signal is of finite duration, right? So this example is an example of a signal which has finite total. And if you want to find out the average, this will be the same 6 divided by infinity. This will be 0. This is an example of a signal which is of finite duration, but its average is 0. This is an example of a signal whose total is infinity, but average is going to be just 1, because value remain constant throughout, right? So two categories of signal. One, a signal whose total energy is finite. The other, this is what we are going to talk about. The first one, finite total energy. Typically, those are signals which remain there for a finite duration. It starts at specific time and ends at specific time, and we can just sum that up or integrate it. And I will be using this integration summation synonymously because they are one and the same thing. Integration is summation of a continuous quantity. So if you have a finite signal, it will have a finite total energy. And the average over the entire minus infinity to infinity period is going to be 0. Second, if you have an infinite sort of a signal, there you would see that the total energy will end up becoming infinity, but in many of them you will be able to find out the finite average power. Like I gave you examples of 1 or 2 signals which more or less remain constant, so this average power remains constant. Any confusions here? Straightforward or complex? It is just giving you an example of two categories of signal. Okay, this thing is important and we are going to spend some time on this. Although these things you may already know from your high school graphs mathematics that you have done so far. This is the concept of time shift and transformations. So what are we going to see here? If we have any signal x of t, the graph that you see or plot that you see right here, if you have any signal x of t, now we can just either shift that x of t by a particular quantity or scale that by a particular quantity. So this a and b, we can have any constants here, and it will end up giving us either the shifting of that signal or it will end up giving us scaling, either compression or expansion of that particular plot. So let's see. So here, if x of t is this, then x of t plus 1 is going to be a shift left by 1 time unit. So this is just shifted left by 1 time unit. So if you see this graph, this is from 0, 1, and 2, and this actually gets shifted left by 1. And similarly, if we had, let's say, x of t minus 1, this is shift right by 1 time unit. It will end up giving you a graph which is going to be something like this, starting from not 0, starting from 1 and ending at 3, right? So this shift left and shift right, if it is t minus something, it is shift right. If it is t plus something, it is shift left. So shifting is straightforward. We can have x of t plus anything, it is going to be shift left. X of t minus anything, it is going to be shift right by that time units. The other thing is basically scaling part. So if x of t is this, if we just have x of half t, x of 0.5 t, it is going to be compression. Then it is your signal will get compressed by that much amount, and here you have the same thing at 0.5, right? So, and again, if it was 2t, it will be expansion. So one is expansion and compression. The other thing would be The time flip. Now what is the time flip or axis reversal? So x of minus t or multiplication by -1. So that thing would be something like this. The whole graph gets flipped, a mirror image. So 0 and -2. So this whole thing gets flipped. If this was the graph here, it will just get flipped. The axis, t-axis, sort of rotates. So these are simple concepts that you will see, and I will just give you multiple simple examples. For example, if we have a graph like this, max at 1, and this is starting at, let's say, 3, this is 4, and this is 5. If this is x of t, then we will see that what happens at x of minus t. It would be just the whole thing gets flipped. Instead of starting at 3, it will start at -3 and end at -5. Right? So this is minus t. And similarly, if you want to see the shifting part would be, let's say, x of t plus 2. This is going to be shift left by 2 time units. It is going to be something like this, starting at 1 and finishing at 3. And similarly, if we have x of, let's say, t minus 1, it is going to be right shift by 1 time unit. So that means it will start at 4 and finish at 6. Right? So these are simply few things that you will come across a lot. So you already know a signal which is, let's say, u of t. We saw that u of t, this was a unit step signal. So u of minus t. Yes. Yes. Remember this. This duration is past. I think I talked about it earlier also. Remember this throughout in engineering. Once we plot the time axis t here, this denotes the past, this denotes the future, and this denotes where you are right now. So t minus 1 is actually shifting right, t plus 1 is shifting left. In time axis, there is no concept of negative time. There is no such thing as -1 second or -2 seconds. But in this plotting, we always end up getting this -1, -2. What is this -1 and -2? We are right here. So this whole, let's say, y-axis is traveling, this whole y-axis is traveling this way. And right now we have reached this. And in future, this whole axis is going to move on that side, left side. So this is true not only for discrete time, for continuous time, for discrete time also. You will see that sample number 0 is the sample that we have obtained right now. These are the samples that we obtained earlier, and these are the samples which are going to come in future. These are past. And whenever we have x of n minus 1, it is actually delaying it, shifting it right by 1. And whenever we have n plus 1, it is shifting left, it is advancing it. So the whole time axis being advanced or time axis being delayed by 1 time unit. This is basically the concept, and this will become clear as we take examples. You will see that the whole thing becomes more clear. So multiple different examples we will see later on. So this is basically a concept which will be excessively used, especially the scaling part we will hardly use, but that B part, which is the time shift part, shifting right or shifting left. This is what we are going to use a lot. That if we delay a signal, if we just shift a signal left, shift the signal right, so what happens and how does it look like? So that is something that we are going to do a lot. Okay, so these were sort of few new things that are covered in this slide set number 2. Rest of the things we have already covered, but let's just for the sake of it go through it again a bit more detail. We already covered The periodic signals, what's a periodic signal? A signal which repeats itself. So this is an example of a periodic signal that it just repeats itself after any particular time interval t. So this is, if it is periodic, then whatever value is there at x of t, the same value will be there at t plus the time period. For that matter, t plus any multiple of time period will give you the same value. If you see this graph, this is basically the graph that you have. So this is one cycle. This one cycle is equal to your time period t, whatever value the thing is, 6 point something value is there. And this is basically 2 times time interval, right? So whatever value is there at any particular time interval, let's say t1, whatever value is there at x of t1, the same value will be there. So whatever value is there at x of t1, the same value will be there at the time interval t1 plus any multiple of t. So this is how we define a periodic signal. So at t plus t1, the same value, and similarly 2t plus t1, the same value. So you'll end up getting the same values throughout. T plus t1, 2t plus t1. So that's the property of periodic signal, that it just repeats itself after a particular time interval. And for that matter, you will see that at any instant we can take a value and you will see that that value will get repeated after a time interval t. So that's a periodic signal which repeats itself. Example is that of a sinusoid, sine or cosine are periodic signals and they have a particular time period. We talked about odd and even signal. A signal is even if whatever is there on the left hand side, the same thing is repeated on the right hand side. So whatever is there on this side, on left hand side we have got a sort of an image of the same thing on this side. Then we say that we have a even signal. So whatever value is there at any instant, let's say t1, the same value will be there at minus t1. So that's a even signal, images of each other. And similarly, we have an odd signal also. Odd signal, we already covered that also. The property of odd signal is whatever value is there at any particular interval t1, at minus t1, the value will be negative of that. So whatever value you have right here at minus t1, we don't have the same value, we have negative of that. So this is how we define a odd signal. Example is that of a sine. So sine t is a even signal. We covered that last time also, just repeating it again. So this is where we are going to spend some time, as I mentioned earlier, exponential and sinusoid signal. So what's an exponential signal? It is of the type seen right here. This is an example of an exponential signal. So we have a value c and we have a value a. C is basically a scaling value and a is that thing which is giving it a particular property. So we can have different examples. First example that we see here is that both c and a are real, and both c and a are real positive value. If both a and c are real positive value, that means a is also greater than 0 and c is also greater than 0, both positive and real number. So you will end up getting what is known as a exponentially growing signal. So it is just exponentially growing, and this subscript you will see will be actually c right here. So it will cross that 0 axis at c. So this is an exponential signal with both c and a as positive, exponentially growing signal. Now, if we have a which is negative, so this is an example where we have c e raised to power of let's say minus 2t, something like that, where a is a negative quantity. Then we have an exponentially decaying signal. And again, interestingly, this crossing point remains the same, which is c. So these are two examples that we can see for a exponential signal. So let's take an example of 2 e raised to power of let's take it 3t, 2 e raised to the power of 3t. You will see that it is going to be an exponentially growing signal, something like that. And this subscript here will, this intercept here will be 2, and this is your t. And if we have, let's say, let's take a negative value also, minus 2 e raised to the power of 3t. So it is going to end up giving you a graph which is going to be something like this, and this intercept here will be minus 2. Both of them are exponentially growing, one going toward the positive side, the other going towards the negative side. So the other thing, let's take an example, e raised to the power of minus 3t. So how does that look like? This will be an exponentially decaying signal, and this intercept again will be 2. And interestingly, this never touches 0. Exponential signal actually here never touches 0 and goes all the way to infinity. It never actually touches 0, comes very close to it, but never really touches 0. And similarly, if we have, let's say, minus 2 e raised to the power of minus 3t, how does that look like? So we can just plot that here. It is again going to be a exponentially decaying signal, something like that, this becoming minus 2. And again going all the way to infinity, never really becoming 0. So these are examples of exponential signal where both C and A are real. Then comes our interesting example where we see a complex value for A, and not only complex but purely imaginary value of A. An example of that would be some scaling factor with this thing. Now this complex exponential, I think I talked about it last time also. Become comfortable with this. This complex exponential, we have multiple names for this complex exponential. We call it complex exponential, we call it complex frequency, and at times some writers also refer to it as frequency. So why is that called as a complex exponential? Because in exponent we have a complex value right here. A is complex. It is basically a complex quantity. And why do we call it as complex frequency? Because Euler actually gave us that the real part is also a sinusoid, the imaginary part is also a sinusoid. Both of them are basically a sinusoid or a frequency, you can say. And again, what is that frequency? Now this omega naught that you see, omega naught can be any constant, 2, 3, 4, 8, 10. So this omega naught can be any constant value, positive or negative, whatever value you want to give. Normally it will be any value, real value. Now it is very conventional to always represent omega naught in terms of 2 pi multiplied by something. So if let's say we have value omega naught equal to 10, we don't write it as 10. Typically we write it as 2 pi multiplied by something, and that something in this case ends up becoming this over 2 pi. Why we write it this way? Because of this cosine. You remember cosine omega naught can be written as cosine 2 pi f times t. This value which is multiplied by 2 pi is what? This is basically the frequency of that sinusoid in hertz, that how many cycles per second we have. That is why instead of just representing that value as number, we represent that omega naught not as a number but as a value which is 2 pi multiplied by something, because then just looking at it we exactly know what it actually is. And again, not only that, omega naught itself for continuous time we call it as angular frequency. I hope you have already used this term, angular frequency. And f is the frequency which is the one we know in hertz. And for periodic signal, because this is a frequency of periodic signal, we are interested in time period t. And time period t, that what is the repetition time period? And this repetition time period is again linked with both omega naught and f. It is basically equal to 1 over f, or in other words we also call it as 2 pi over omega naught. this is the repetition time period in seconds, that it repeats itself after how many time duration. So these are basically some linkages which you may already know, but we were interested basically in the complex exponent. So complex exponent has got a real part and imaginary part. Both of them, Euler gave us this, that they are basically sinusoids, cosine and sine. Now, because cosine is also periodic, sine is also periodic, and we have the same time period for cosine and sine, that means we will have the same time period or repetition period for the complex exponent also. And because both of them, real part and imaginary part, are periodic, this e raised to power of j omega t or complex exponent is also going to be a periodic signal. And the time period we can find out, it is going to be t, and t will be equal to 2 pi over omega naught, right? So these are few things about complex exponent. I mentioned these things earlier also. So just this was more of a repetition of the same things. Now we saw one example where we had both C and A real, positive or negative. We saw another example where C was real and A was complex but imaginary only. Now let's see an example where both of them are actually a complex quantity. If both C and A are complex, then how would it look like? How the signal is going to look like? So our original signal was C e raised to power of at. If both C and A are complex, then we can represent C either in terms of polar coordinates or in terms of rectangular coordinates. So if we just represent C in terms of polar coordinates, magnitude part and the phase part, and A in terms of rectangular coordinate, this is basically the real part and imaginary part, then just plugging these values back in here, we'll end up getting this whole long term right here, right? So C e raised to power of jfi e raised to power of r plus j omega t. Again, looks complicated, but we know that we can just combine the two exponentials together. We can combine these two exponentials together, and then we can just separate the part with j and a part without j and write it this way. So we end up getting a quantity is shown right here. So in this quantity, this is basically some constant into e raised to power of some constant time t, the same exponent, the real exponent that we have already seen, and depending on the value of c and r, it would be something like either this or going down like this. So depending on the value of r, whether r is a positive value, if r is positive, it is going to be like this. If r is negative, it is going to be something which is going to be coming down like this. And this intercept would be your C part, right? And the other thing that we have, this is simple complex exponent. And with j, instead of one constant, we have a constant plus another constant. So some constant value, e raised to power j times something t. So this can be taken as simple omega, this can be taken as ABC, whatever you want to call it. It is just a complex exponent. And we know that how a complex exponent looks like. We have a real part and imaginary part, both of which are sinusoids. So cosine of this thing would be a real part, and the imaginary part will be sine of this thing multiplied by t. And if we just put a scaling factor with both real and imaginary part, this is that scaling factor with the cosine, the real part, and this is that scaling factor with sine, the imaginary part. And we can plot this real and imaginary part separately. Cosine, if you plot, it will be just a sinusoid. But now the magnitude, instead of remaining constant, magnitude is changing like this. With time, the magnitude is changing. So if you see here, this is that changing magnitude with time, the exponentially changing magnitude, right? So this is that magnitude part which is changing with time t. That as the time progresses, the magnitude is changing. And similarly, if your R was not positive, if R was not positive, it was negative, then you will end up getting a decaying sort of a magnitude right here. So very first look, this whole thing looks quite intimidating, quite complex. This whole cosine looks quite intimidating and complex. But if you just take them one by one, it's a sinusoid, cosine. Okay, let's plot sinusoid. And the magnitude part, what is the amplitude of that sinusoid? Instead of having a constant amplitude where you have just a simple sinusoid, we have an amplitude which is changing with time, exponentially changing, either exponentially increasing or exponentially decreasing, or we can say exponentially growth or exponential decay. So this first sinusoid and second sinusoid are basically examples of these complex exponent, where both C and A are complex values. And this is basically decreasing amplitude, this is basically increasing amplitude. So decreasing sinusoid or damped sinusoid, this is basically amplified sinusoid. So two different examples. Any confusions here? So complex exponent, now more so for electrical engineers, because electrical engineers then use these complex exponents and all that combination permutation of complex exponents in their higher level courses a lot. Computer engineers don't use it that much, but they have to know what complex exponents are.